results for Ricci curvature, part 1.
Okay, thank you, Jeff, and really thank the organizer for the invitation. I'm really happy for be part of the program. I think I was so excited about it. Probably John told me I was the first one applied to the program. And I got the first one to try this fancy. When I prepared for the slide, I thought, oh, only if they have 2 screens, but now they have 3. Okay, we'll see. Okay, so actually I would like to start with something really everybody already know. What's the name, what's Ricci curvature, what's comparison, and introduce one of the most fundamental comparison, namely the Laplace comparison. And I promise, so this all maybe sounds like everybody already know maybe. I promise in the end we will see something new actually, hopefully. Okay, so-called 2-point comparison in this case. Okay, so let me start. So what is a Ricci curvature? Actually, Carsten already talked about the sectional curvature. So Ricci curvature, we can think of actually Ricci tensor, more precise. It's just trace of the full curvature tensor. So the nice thing about this is it's a symmetric 2 tensor, just like the metric. The metric, Riemannian metric, is a symmetric 2 tensor in this case. So the name actually, Ricci, it's named after the Italian mathematician, Gregorian Ricci. His full last name is Ricci or Cabastro. And I think in one of his famous papers, only in one paper, he short his last name, and that's well. I think it's nice. I don't want to call it too long. So Ricci Cabastro, Ricci curvature. Okay. So in the bond, we often actually talk about a Ricci curvature instead of Ricci tensor. The Ricci curvature is evaluate the tensor at the unit vectors when x is unit. So it's really just some kind of average of the sectional curvature we saw. And okay, so when average, we usually divide by the number of things to add, but traditionally we don't divide it. So that's at least lots of book has tradition. Some other book does divide by taking the real average. So in my tradition for sphere, the sectional curvature is constant 1, but the Ricci curvature is constant n-1. So in lots of, if we statement, you will always have this n-1 in there. That's because we take in the sum, not the real average in this case. But it's some kind of average, right, in this case. Okay. And so Ricci curvature we can see the definition. You can take another average. It will be so-called scalar curvature. So Ricci curvature, which is in between sectional curvature and scalar curvature, so right in the middle. And what is a median? Okay, so the sectional curvature we see, it controls the distance. And the Ricci curvature, it measures the deviation of the so-called volume element. So it's more related to the volume instead of the distance because we are taking some kind of average. So if you take the volume element and take the expansion, at the point, the Taylor expansion, then the first term is the same as Euclidean, second one term is exactly the Ricci curvature. So the Ricci curvature really captures that, measures the volume element. Okay, all right. So that's the Ricci curvature. Maybe I may sell what is the Ricci curvature, why the Ricci curvature is special. Again, it's also special is that in the Einstein equation, we have Ricci curvature, so I only write in the vacuum one. If we have cosmological constant, then the equation is just the Ricci tensor is constant multiple of the metric tensor. And that's special because we said Ricci and the metric tensor are same type. They are both symmetric tensors, so we can make an equation out of it. And we can also, in the Ricci flow, of course, so notice we have 3 in case, I think this is first one. That's usually the one after, and this is the last one in the case. So in the Ricci flow, we have, of course, the Ricci curvature. And it's also related to many other things. For example, optimal transport in applied math in this. So this part actually, I think Andrew will give in another talk. So I will not mention here in this case. So it's really not just the geometry. It has lots of applications. Okay, so that's maybe what's the Ricci curvature and what it means. Now, just what is so my title is Comparison Geometry. For comparison geometry, so we already see in the first talk, you try to compare to the model. In here, in my case, the model will be an n-dimensional, it's the same dimension with a manifold, simply connected manifold with constant sectional curvature. In the last talk, we see the model is two-dimensional. Actually, sometimes you can also think of one-dimensional, but so let's just make an n-dimensional model, okay? So this model, right, after scale, really, we only have 3 space. So, and the good thing why we compare the model is we know everything about the model. These are really concrete space, everything here. So we can try to use a model to understand the manifold. Okay. So in general, the setup is you can some kind of curvature doesn't matter. If you have curvature low bound, or you can also do upper bound. In my talk, will be always focused on lower bound. In the case, you compare this space with a model, as we saw before in the last lecture in the thing. So the general principle is, if the big curvature is big, that means it's small. You need so the size is kind of small. So that's the general thing. We see lots of example. In particularly, I think we saw it in the sectional curvature, right? In the Topologov comparison, we saw in the last lecture. Or I think if we, in the first year geometry class, we often saw the Ricci comparison, actually. Ricci comparison is some kind of, you can think of infinitesimal version of the Topologov, okay? So in this, for my comparison, so we want our focus on Ricci curvature in this case. I want to introduce another infinitesimal version of Ricci comparison. So take one more derivative, and that's so-called Hessian comparison. So this is for sectional curvature still. Hopefully, just relate to the previous talk. So Hessian of a function is, again, a symmetric two-tensor. This is a definition, just the covariant derivative of the gradient in x and y. So in this, we can see it's a tensor, but if you do a little bit of work, you can also see it's a symmetric two-tensor in this case. Okay. So the Hessian comparison is, we can state as following. That's a different notation. In the last talk, we said Carsten used sec for the sectional curvature. I use k. Since I used k for sectional curvature, so I use h for the bond instead of k. So hopefully that's okay in the difference from the last lecture. So h will be my bond in this case, in the whole talk, because I used k for sectional curvature. For sectional curvature, the hash is, so I think a very, very important LC is the distance has lots of information about all the geometry. So Hessian is, you take Hessian of the distance function. And distance function may not be smooth, so you can understand at a smooth point. Even at non-smooth point, you can understand in weak sense. Maybe I'll mention that later. So C is, if you took Hessian of the distance function, and you do, so here I just compare with the vector, which are unit, and the vector is perpendicular to the distance function. Because along the distance function, the Hessian is 0, so it's not interesting. So we just, so in here, I have the point. I think my function is x is fixed, and this is the y. So this is a vector at y, the tangent vector in this case. And you do the exactly same thing in the model space. We set as a model in here. And you look at the distance function and the unit vector, any unit vector, which also, perpendicular to the distance function direction. And then the Hessian we set in the curvature, the big curvature is smaller than the one in the model. And that will be the key. Okay. So, this is maybe not full. This is just as an infinitesimal version of the Ricci comparison we all see in this case. So that's. The only thing is you need a more derivative. So this does not make sense in Alexander space, I guess. Okay. So, but this from here, we can intuitively see then for Ricci curvature is, since it's a kind of average of sectional curvature, So we have introduced so-called the Laplace comparison, which is which I claim, this is a really, most fundamental comparison for Ricci curvature, for manifold with Ricci curvature. So now I have a Ricci curvature lower bound. Then again, look at distance function. Here's a Laplace, which is just a trace of Hessian. I forgot. So Laplace of U is just a trace of Hessian. So that's since for sectional curvature, you have a Hessian comparison. So I guess intuitively you can think we have the Laplace comparison for Ricci curvature. Okay, and this is really very useful in many applications. In the simple ones or in the complex like gradient anatomy, I will talk more later. So I want to emphasize this is really also the Ricci curvature lower bound. You can be characterized by the Laplace comparison. The only thing, of course, not good is that this you need a derivative, so you cannot make sense in metric space. But for manifold, this is, and we can see this easily by just take the Taylor expansion of the Laplace of the disk function, and the first term it again will be same as the Euclidean space. Then the second term is the Ricci curvature. So therefore, if you have this, then this is equivalent. Okay. So this one is actually so important, I feel, the Laplace comparison. I might actually present a proof. And maybe this proof, you haven't seen it before. Okay, so I should say this has many proofs, the Laplace comparison. So there's, okay, so far, any questions? Okay, so we say in this, it's very important. It has used key. It's in the Cheeger-Gromov splitting theorem, which I will not talk about. This is also very important too for studying manifold with lower curvature bound in this case. Okay, so I might come back a little bit later. So how was this one of the proof actually in this? I maybe go back to introduce really the fundamental equation for Ricci curvature. This is maybe one or the second. So which is a Bochner formula. So another one which is equivalent. Basically saying for any smooth function, or I guess as long as you can take third derivative, you don't have to be. For any functions, namely if you will take the Laplace of the gradient of the function, then you can think of switch. Switch is a derivative. Here is a Laplace gradient. This is gradient Laplace. When you switch around, usually curvature comes out, and since the Laplace, so actually Ricci curvature exactly come out in the equation. And not only that, and the term actual come out is a Hessian, it's a square term. It has always a positive sign, so it has a definite sign. Okay, so the amazing thing is that this is true for any functions in this. I think in the first. This formula, you just switch the derivatives. Well, it still looks complicated. I mean, there's so many derivatives. But it's good that we said you can apply to any functions. So you can apply to some functions. For example, if we apply to harmonic functions, then this will be 0. And since just to simplify. So if we apply to harmonic function, this term equal to 0. And then you usually have nice equations. Or you can apply to distance functions. Distance functions, the gradient is constant. So that means the left-hand side is 0. So gradient is constant. So that simplifies in this case. Or eigenfunctions. So anything, you can apply to many special functions and get many important equations application. That's how. And we're going to actually apply to distance function in a minute. Let me just see also this why it's important in this. In another factor, if you have a really special function, namely the function is harmonic and has constant gradient. Okay, so that means this is 0 and that's equal to 0. The 2 is term equal to 0. So we get Hessian square plus Ricci is equal to 0. Okay, so now let's assume the Ricci is non-negative. I have a lower bound. Well, that this positive thing plus greater or equal to 0 equal to 0. That means the Hessian has to be equal to 0, right? And if the Hessian equal to 0, if non-trivial, then the gradient vector is a parallel vector field. You have parallel vector field. That means you have splitting. So this is really the starting point of the Chico-Gromov splitting theorem. You can see. Then the goal is to construct, this kind of harmonic function, which looks like a distance function. Okay, so we can really read off from the formula. Okay. So this is true for really, any form. Now, in the case when we have the Ricci curvature bounded from below, well, we can plug in here. And how do we apply is, so in here, this formula is a Ricci curvature. Let's say if we bound from below, so you're replaced by the Ricci curvature lower bound. And you have this. And the Hessian term, we can combine using the Cauchy-Schwarz inequality. You can change it to the Laplace. Okay, so that's Hessian. So we call this Bochner inequality. Okay, so if you have Ricci curvature bounded from below, then now it's for any function, you have this Bochner inequality. And this also completely captures the Ricci curvature lower bound. You can use this to define Ricci curvature lower bound, except, again, you have to take many derivatives. So, yeah, this characterized Ricci curvature lower bound, what it means is we see that if the Ricci bounded from below, then we have this inequality. We already, if we have Bochner formula, we see trivial have this. Now, if this Bochner inequality holds for all functions, then I claim that then this manifold has Ricci curvature lower bound, really. Okay, so you can see also quickly, how do you see? Well, this is for all functions, so any point, any direction, you can choose a suitable function, plug in to this, you have the inequality, and combine with Bochner formula, you got the Ricci curvature information back in this case. Okay, so this is, I think, maybe more general about Ricci curvature lower bound. See, lots of results we can derive from here in this case. Okay, now, as we said, I want to present the Laplace comparison. That's the key of the lecture. I want to give, this has many proofs, so this is one of the proofs using the Bochner formula. We already saw the Bochner formula. Now we're going to apply to Laplace comparisons about distance function. So let's apply to distance function. Let's take the function to be the distance function. Just assume it's smooth for now in the case. So for the distance function, the gradient is constant, so left-hand side equal to 0, right? In this case, now everything is here. And this I rewrite it to be, so this is a derivative in the gradient of R in this. So I have this is the gradient, the radial direction. Actually, let's just look at this point. This is a radial direction. So in the product with the radial direction, I'll just say this derivative is in the radial direction. We have the Ricci curvature. Okay, so that's for distance function, you can always true. So now you look at specialize in the model space. In the model space, the Cauchy-Schwarz inequality I wrote before. Okay, it's yeah. So Cauchy-Schwarz inequality is equality because it's the matrix is just a diagonal. And another thing is the Hessian of R. This is special for distance function. Is in the radial direction is when we have 0 in the radial direction and it's a red. So the matrix is really m inside here is m minus 1 times m minus 1 instead of the 4 m by m matrix. So therefore, when I use the Cauchy-Schwarz inequality here at the bottom, it's really we can take m minus 1 instead of the n we had before in the case. Okay, and this is equal for the model case. That's the Cauchy-Schwarz is exactly equal. And in general, we have inequality and replaced with Ricci curvature bound. So we have Ricci inequality and then Ricci equality, and it looks like this is a ODE. So nonlinear. We should have the comparison exactly. Okay, so that is an idea. To write out precisely, notice that the distance function at the point x at the origin is blow up. It's not defined. So to write, it's somewhat a little bit to write. I means there's a ways to do it, kind of little bit complicated. I'm not sure. So I'm going to present the proof. Hopefully, we don't have, I thought it's very simple. We don't have to deal with that. Okay. So natural thing to compare, well, usually is let's take the difference of these two equations. So that's good, great. I was hopefully, remember we have these two equations here. One is equal, one is, let's take the difference, okay, just to subtract them. So h is gone, and that's the derivative of the difference is bounded by the square, okay, in this case. So we got 1. Well, so when you compare, either take difference or take the ratio in this case. And in the, I'm going to introduce a notation so that we will use later and in my even next talk in this. So this SNH is really like a sine function, which satisfies the second order equation and vanish in the starting is 0 and the derivative equal to 0. So just think about it as a sine. If we don't have the h, it's just as a sine function. And when the h equal to 0, it's a r in this case. You can solve explicitly. Using this notation, then the model space, the Laplace of the model space, you can write out explicitly because we said we know everything about the model, so we can write it out in this case. Okay, so this is two equations. I should have named them: the difference of the Laplace and this. Now to prove the Laplace comparison, let's see where we have this equation. What I'm going to take the difference. Okay, take the difference of the Laplace, and now I'm going to, in the front, multiply by the function we just have, the sine function. These are, you can think of with a Jacobi, if you look at the Jacobi field of the model space, those are the coefficient of the Jacobi field vanishing starting from 0. Okay, so you multiply this. Okay, so, well, you take the product rule, take the derivative of the sine here, and take the derivative of the second. So that's it, product rule. Okay. Now in here, maybe this part I feel, it's couldn't to write out. Here is a derivative. Remember, we have the derivative less or equal to inequality. And that's a square, so we can plug in. And this derivative, we can use replaced by the Laplace. So, okay, so this is, well, the first term here, we replace, I should write out maybe the color. This one replace the Laplace. The second one here replaced by the equation. We still have it here, great, in this case. So I just use these two equations and plug in. We did not do really anything, right? So it's less or equal to. Is it? Now what, if you look at a little bit carefully, and this actually is a complete square. This is equal, notice. So really, when you do equal, you cannot do anything, right? So this is, you pull out the sine square and n minus 1 square, and that's complete square. And they have negative less or equal to 0. Okay? Well, that gives the Laplace comparison. Because if we take the integral, the sign, remember, at start 0 is equal to 0, and this one is bounded. So it's start integral 0, and look at the integral at s, you have this, and it's a Laplace comparison. Okay, so I'm not sure, I thought maybe this proof you haven't. And this, actually, we got this proof by when we studied the trying to generalize the Laplace comparison to Bakry-Emery Ricci curvature, which will be in the next talk. So from that work, we actually come up with this proof. So I thought it's relatively clean in this case. Okay. So that is a Laplace comparison. Okay. So as we mentioned before, this has many applications, and in lots of complicated one, or in the let's say the Bochner theorem, we know when the Ricci uniformly bounded by positive, diameter is bounded by the model. It's a comparison in this case. Now, if you use Laplace comparison, it's just one word, one sentence. Say if you have the distance, it's more than the model, x naught and y naught. Let's say realize the maximal diameter. If the distance is bigger than this model, pi, let's say h equal to 1. It's bigger than pi. So then you look at the point. This is pi. You look at the point just before the pi in this case, right? By the okay, so if this is minimal, then the Laplace is well defined. It's smooth at this. This is well defined. By Laplace comparison, is saying it's going to be less or equal to the one in the model. H equal to 0 in the model at the point pi. In this model, we said what is this? It's just a S sine over the derivative sign over S and H. Well, there's n minus 1 here. So this is just really a cotangent. Cotangent blow up at the point pi. So that cannot be true. And that's contradiction. Okay. So it's really, 1 volt in this case. And these I listed them because they are really very, very direct. And also, we can have the Dirichlet eigenvalues comparison. Again, the space with a Ricci curvature bound is bounded by the model, and the heat kernel is is greater or equal to these are with the Dirichlet boundary condition in this case. So we will talk about the Neumann condition a little bit later on in this case. Okay. So that's very, very direct applications. Another very important application is because the Laplace comparison gives, we said, Ricci curvature controls the volume element. It gives a volume comparison. Okay. So what's the relation between them? The relation between the Laplace, so for any manifold, if I write the volume element now in terms of the polar coordinate, geodesic polar coordinate, so in the r direction and the theta direction, then the log derivative of the volume element is exactly just the Laplace of the distance function. Okay, so that gives a connection. Therefore, if we have the Laplace comparison and use this lemma, we get very quickly the ratio of the volume element compared with the one in the model is non-increasing. So we have the monotonicity property. Well, as we said before, we said Ricci curvature controls the volume element, and that's usually, if you take Taylor expansion, it's just a local property. Now the great thing about this is global. You can, as long as this is going out minimal geodesic, you can go far away and still it's a minimal in this case. Okay. Once we have volume element, okay, well, we can have the real volume comparison. So this is a Bishop-Gromov volume comparison, we said in the last lecture, also mentioned in this. Namely, the volume of the manifold compared with the volume of the ball. This is the volume of the ball in the model space is non-increasing in R. Okay, and again, this is very useful. And sometimes, okay, so we call this is also very important comparison. And for Ricci curvature, so I feel, the Laplace is like the heart of the person, and the volume is like your hand, and you can see it more quickly in this, but really it's coming from your heart in this case. Okay. So this is monotonicity is always great. So we can write out the monotonicity. That means, and actually I write out the monotonicity, and you let one of them go to 0, it get absolute value comparison and get the volume doubling in this case. Just rewrite this out a little bit in this case, the volume comparison. Okay. So this comparison also has many, many applications. So I'll just list one of them already, I think, mentioned in the last lecture. Volume doubling in analysis, it's also very controlled in the case. Yeah, moreover, if you also have rigidity, also in all the comparisons, is if it's equal, then it's exactly isometric to the model in this case. So once you have rigidity, you can all study almost rigidity and so on. So let me mention just a few applications, I'm not sure. So for example, one application just to really only use volume comparison, that's the application I'm focused, is in terms of topology, we can control the growth of the fundamental group for manifold with non-negative Ricci curvature. Namely, any finitely generated subgroup has to be grown like a polynomial in this case, because the volume because the volume in the, well, actually, right, we have used, because the volume of this is controlled by the model. When h equal to 0, the model is Euclidean, which has the polynomial growth in this case. So any space the volume has a polynomial growth actually turn out control on the fundamental group because we can go to the cover in this case, so point-wise. And the Gromov's compactness theorem in this, we already see from the last lecture, namely, if you have Ricci curvature lower bound, then it converges. The Gromov-Hausdorff convergence, which is volume comparison. And we can use that to give a first Bethe number control. So in the last lecture, we see the sectional curvature controls all the Bethe numbers. Ricci curvature only controls the first Bethe number. So there's a counterexample to second Bethe number and high ones. So Ricci is weaker in that sense. So all of these, it's really just a volume comparison. Also, I'm not sure this since maximal diameter theorem. Remember the diameters, the Bonnet-Meyer diameter, we said if the Ricci curvature is greater or equal to n-1, then the diameter is, use a Laplace comparison, we see this. Now we said if in here, so now the maximum one, if the diameter actually equal to pi, then this is the manifold is isometric to the sphere. Okay. So that's called maximal diameter theorem. In his original proof, use analysis to do it. Actually, you can Shiohama give a proof of the volume comparison, showing that the volume is also maximal, then not just the diameter. Therefore, by rigidity, it has to be sphere. Okay, in this case. So this show maybe the relative volume. We can also show for any manifold non-compact, if the Ricci is greater or equal to 0, then the volume has to grow grow at least linearly. So okay, so I means all of this is because they are direct consequence of the volume comparison, and there are many other, in the we said this is the Gromov convergence theorem is the starting point, and the Cheeger coding has many theorems after this to use. Okay, so this application about any questions so far? Okay, so this part, I think all of this is somewhat maybe this is a modern code. I mean, we can call those a modern, but maybe we can call them a classic comparison in this case. So now I would like to maybe talk some kind of very recent comparison, actually mostly used by Ben Andrew and Clark-Beck. So they didn't formulate this way. I kind of reformulate trying to connect with what. It's kind of also the Laplace comparison we saw before in this. So what is the difference? The difference is the Laplace comparison, well, it's about distance function. We said, well, in that, we fix point, that one point change, right? Here is you let both point changes. So we count this is 2-point distance second derivative comparison. Okay, so namely, and there you can do it with multi-point and so on. So yeah, the Laplace, the distance function when we do is a Laplace, we fix the 1 point. Now we're going to do let both point changes. So what is this EI is very important. EI actually is defined. You take a vector here, which is perpendicular to the radial direction, and I parallel translate to y. Okay, so therefore these vectors are defined along the whole geodesic, at least both at x and y. Once I have x defined, my y is also defined. So EI is, you can think of it along the geodesic or at least, so they are connected both. So when I do the variation, I take the distance function and I take the derivative with respect to EI. It's really x and y are both changing. Okay, so in Euclidean space, well, this is just x and y, and here is EI and EI. If it's perpendicular, so in the Euclidean space, then the distance does not change, right? I is just the distance here, and this will be like this. So the derivative will be equal to 0. It's a constant in this. So it's very important. I emphasize the difference here. The variant is 2 point is x and y are both changing. Okay, in this case. Okay, so in Euclidean space, maybe you can see is this Rxy is in the when you let them change, it's actually this is equal to 0. Well, it's a constant, so the derivative equal to 0. Okay. So I only write out the direction, which again perpendicular to the radial, because radial direction are easy to figure out in this case. So now we take the sum in all these directions which are perpendicular. And this, I don't know, it's not exactly Laplace, but it's really like a Laplace type, right? You take the summation, and claim is that then this is also less or equal to, you do the same thing in the model space. You take the distance function and you vary. And in the model space, you can compute them explicitly again. You can, the equal to t. T is like sine is like a sine. So this is a cosine. It's almost, you can think of just tangent. Okay, in this. So it's a negative of the tangent. And r is a distance between 2 points. So it's the distance over 2 in this case. Okay. Actually, the proof, this again, just like the usual Laplace comparison, you can use variation very quickly, just compare with the model. And I feel probably lots of experts already know. Okay, but I found in there, really found as a useful. Yes. Okay, how this used? This is really, I think, can view like a Laplace type comparison, but with a 2 point. Okay, before how it used, I would like to compare to the usual Laplace before, because I need to do a little bit more. We want not just apply to the distance function, but apply to a function which composes with distance function. So this is like we call it radial function. It's a function composed with distance function. So for Laplace comparison, we can very quickly extend to, because the Laplace in polar coordinate is, this is the Laplace from the sphere, and this is a first derivative, second derivative in this. So if I have a function phi taking Laplace in this, right, because it only depends on radial direction, this is equal to 0, and that's its, so maybe let's write it out. So the Laplace of a function which is in the radial, it only depends on distance. If we plug in, it's really just the Laplace times the first derivative plus the second derivative in the radial direction. Okay. So now do the same thing for the model. Okay, in the mod, so what this is matches. Now, if I have a sign on the first derivative, if my first derivative is positive, then you have the same comparison in this case. And if my first derivative is negative, then we reverse the comparison, right? So really, we automatically have a comparison for function, more general, not just the distance function, a function composed with distance function, as long as they are sign. And another thing I maybe not emphasized before, we said we only do it at smooth point, and you can make perfect sense at everywhere in weak sense. In weak, whatever the weak sense you want, usually is so-called Berry sense, viscosity, and distribution sense, which is an integral. And for this 3 weak sense, maybe years before, there's a nicely related. The relation between them, I think this spend some time trying. The Berry is always stronger than viscosity. So if you have true for Berry, it's always automatically true for viscosity. And the viscosity is equivalent to distribution. So nice thing, in any of these weak sense, you can use maximal principle. So it's still good. So really, the Laplace, you have a global Laplace at every point with radial functions. Okay, so now we can do the same thing for the one we just had before, the distance. Now we're going to apply a function composed with a distance function, just like before, right? I will only do the case when the derivative of this is greater or equal to 0. You do the same thing like before. So now, instead of this is the one in the model, it's going to be times the derivative. Because here I did not put the radial direction, so we don't see the second derivative here, right? My summation is only in the direction perpendicular, so that's all it come out in the model space. And this comparison, I mean, I thought it's really also very amateur. It turns out really useful to estimate so-called modulo of continuity or oscillations. Because when you have 2 points, okay, so in lots of things, so-called gradient estimate is very important. Gradient is change of the functions. And while this is 2 point changing, how fast are changing? And that's why the distance is 2 point. I feel it's very, very useful. Well, in the beginning, I'm not an analysis people. This model of continuity kind of scared me off, but it's really now I feel it's very, very natural in these 2 point functions. So there's actually many applications. Ben Andrew have a survey article in lots of. I'll just show you one application because it is really comparison. So one application is about the Neumann eigenvalue comparison. We saw the Dirichlet is very quick, use Laplace comparison. Okay, so what is the Neumann? Okay, so it's actually in here. Let me just assume the manifold is closed. You can take compact with boundary, but it will be Neumann boundary, and the boundary should be convex. But that's okay. So we actually think maybe see it before. Again, you have Ricci curvature lower bound. Then the non-trivial first eigenvalue of the manifold is greater or equal to the one in the model. Okay, so what is the model here is you can visualize in the one-dimensional model of the eigenvalue of this outlet. This is actually just in the model. So it's still is second derivative, first derivative on the interval. D is the diameter of the manifold with the Neumann boundary condition. Okay, so the eigenvalue of the space is always greater or equal to this model. Okay, so maybe I phrased this kind of abstract, but actually, let me go to the next one. Is here. Okay, so we still have the result, and let's take H to be positive. I think then we see lots of before. This is just as original with Laplace as an eigenvalue comparison. Then the eigenvalue is bigger than the model. And let's take H equal to 1, okay? And then the eigenvalue is bigger than the model, which is the sphere. Sphere is M, okay? And this proof actually is very quick. You can use Bochner formula to the integral, and you can get it, okay? But only works for H positive in the proof. Okay, so when the thing is that this one, it works for all H. Yeah, H positive, negative, 0. So this when H equal to 0, this is the Zongyang's eigenvalue comparison. Namely, the first eigenvalue it's always bigger than pi over d squared. Okay, and it's also optimal. This is based on Liao's early work in this. So heavily on gradient estimate, and the proof is become quite long. Actually, it took quite. Kind of more, it's uses sophisticated auxiliary functions. So in the general case, for all H, I think first time is this first, maybe it's not very well known by 2 Chinese people because they use probability, and it's in a Chinese journal. So it's in 94. And Crook, he did it, use gradient estimate with the general case. But again, the proof is very, very long in this case. Okay. So Ben Andrew and Klockberg, and that's what's in there, they use this modulo of continuity for heat equation to did it in this case. And then Zhang and Wang, again, it's just follow same idea of Bang-Andrew, but instead of heat equation, just use the elliptical equation directly in this case. And really, the proof is a few lines, so I want to show you how to do it, okay, in this, using the comparison we had before, although maybe it's in the back. Okay, so how do we do it? So thing is, as you said, this is a simple comparison and it's a maximal principle. Okay, so how do we want to compare? We want to compare the eigenvalues. So the key is look at the original proof is gradient estimate of eigenfunctions. Okay, so look at the eigenfunction of the manifold and the model we can compare. The model is very simple in the, so you have, and you look at the quotient of the oscillations. So before, this is the oscillation. In the model case, when this equal to 0, it's all equal 0. So it's really, this is also the oscillation, okay, because you compare the distance. So this is a quotient of oscillations. So you might worry when x equal to y, yeah, this is not defined, but let's worry about that later. Let's think, okay, so this is, you can also take the limit, L'Hopital's rule, and so that is still defined, all right, in this case. So this, so the key is just the maximal principle. You look at the maximal point of this function, while the manifold is closed. If the boundary, you can show that it's going to be achieved at the interior. Let me, for the moment, the maximal is achieved at a point. This is 2-point function of the product. Assumed that at a point that it's not equal. If it's equal, you use a limiting process. Okay, so they're not equal, and for convenience, because this distance over 2 is going to come up a lot, so I'm going to use at S0 to be the half in this. So it's achieved at this point. So at the maximal point, well, this is a quotient. Somehow I'm really afraid of take quotient derivatives, but especially, look, second derivative. But at the maximal point, I realize that since simplified geometrically, all the first derivative is automatically 0. So only thing survive is second derivative at the maximum point, okay? The second derivative of this one, the numerator. Here is second derivative of the denominator. And before that, we have the q, the maximal point value, okay? And this is really just a quotient rule if just brave enough to write it out. Don't stop, okay? After the first derivative, we said it's so messy. But at the point, okay, since it's the maximal point, so it's less or equal to 0. The second derivative is less or equal to 0. You do it at all the directions, right? Okay. Now we take the summation. And so, okay, in here, we want to notice that the model space, you can show that it's always, you can, for eigenfunctions, for the model space, you can construct the function actually is odd function, okay? So for odd function, and you look at this, the maximal here, it's going to be positive, and this is positive in here. So we can drop this, so less or equal to 0. And we take summation over here. We take summation all the perpendicular directions. Now we're ready to use that as the comparison we had before, the Laplace kind of comparison for this, right? This is a function composed with distance function, the model space. By comparison we had, this is less or equal to, well, let's move over. So less or equal to the function times this one. The comparison we had before. In this case, maybe I still should write it then, right? The comparison we had before, EI. In the both directions, phi of the distance function is less or equal to negative 2 over, I think, n minus 1 of phi prime and t of h at S0. Phi prime, yeah, that's all I use. We solely place it by there. Okay, so these are all the direction perpendicular to the radial direction. Now I add the derivative in the radial direction. Radial direction are much easier, so you just add it in. Then this become Laplace, and this the left-hand side become Laplace, and the radial direction, you know, you have the second derivative come in of the function, and you have this. And that's exactly the operator we had, the L, the model space operator. Since phi is eigenfunction, you replace they are equal to the eigenvalue times the functions. And this, remember, this is the first eigenvalue of the model. So these are equal to eigenvalue times the model. Okay, so this operator is really the model space. And we have less or equal to, and that's the maximal point you cross out. That's the Laplace comparison. Okay, so really a few lines I want to emphasize before this proof was really complicated. And from this comparison, we got it very quickly. I didn't do it for when you have the maximal achieved at when x equal to y. We said before, this function is still well defined. You do a limit process. It's not that more complicated. It's still good. It still works in this case. Okay. Actually, I think I do end. Any questions on this? Okay, so this first lecture, I think what we want to get is, what is Laplace comparison? Laplace comparison is really important. Hopefully, that's all you get. So next time is I want to generalize to Bakry-Emery Ricci curvature and integral Ricci curvature in this case. Okay, thanks.